This is the talk on stoichiometry. Stoichiometry is basically a math problem in chemistry. So let's get started with this. The first thing we have to look at is how we use chemical equations. Why do we have chemical equations? Why do we do all the balancing we've done up to this point? A balanced chemical equation gives us relative numbers of reactant and product molecules that participate in a chemical reaction. So what those balancing numbers mean is that you have a certain ratio of one product to a reactant. And I'll show you that on the next few slides. The coefficients of the balanced equations give that relative number. So atoms are not destroyed or created, we just rearrange them. That's why we need to balance equations. And so in the case here, this is just an example with carbon monoxide and hydrogen gas. In order to balance this, we need to put a 2 here in front of the hydrogen gas. CH3OH has 4 hydrogens, and as a result we need to have 4 hydrogens on the left side as well. What is meant by this entire chemical equation now, and this is a really important concept to understand and memorize. One particle of carbon dioxide, or carbon monoxide, reacts with 2 particles of hydrogen, H2. And that creates 1 particle, or 1 molecule, of CH3OH. The other side of this truth is the second statement down here. There's 1 mole of carbon monoxide. That 1 mole reacts with hydrogen gas to make 1 mole of CH3OH. Both of these are true. We can have a very, very small scale experiment like in this top part, or the bottom part is more what we're going to be concerned with because we generally measure things in grams and moles instead of particles. So I'm going to show you how to do this bottom part today, what this means. So we talk about mole-to-mole relationships. The important thing to understand here, this is a picture drawing. If we were to take water, and you can run electricity through water, what you get then is 2 different gases. You get a hydrogen gas and an oxygen gas. So the balanced reaction is right here. We have 2 water molecules, 2 hydrogen molecules, and 1 oxygen. And so in a beaker that you have water, you have this water floating around, the ratio will always be the same. You will have 2 parts of water. You will get 2 parts of hydrogen and 1 part of oxygen. So those ratios always stay the same. That's really important. Here's another example. In the reaction below, if you were able to react 3 moles of methane, so we have 3 moles here of this stuff. How many moles of water would be produced? Well, here's water over here on this side. And so we set up a conversion factor. So we have 3 moles methane. We set up a conversion bubble in order to find this out. Now, some of you, you're probably sitting there saying, yeah, it's really easy because you have 3 parts here. You're going to have 6 parts of water. And you're right, but they're not going to be this easy all the time. So we set up this conversion where the ratio is 1 methane equals 2 water. Whether it's molecules or moles, it doesn't matter. In this case, we're working with moles. So what we do is we put 1 mole methane on the bottom, and that's equal to 2 moles of water. So now, just like we've done a million times before with these conversions, we take the value is 3, multiply it by 2, and divide it by 1. So 3 times 2 divided by 1 equals 6, which is what you saw here anyway. This is the stuff in the conversion is the stuff you're going to need to know how to use better. And so here's a general format for stoichiometry, the steps in solving these problems. So if you don't get anything else out of this video, I would get this part here. That's the most important thing I'm going to talk about. What we do is we start with, generally the questions that I'll ask you is a mass-to-mass relationship because we can measure grams. And that's how we do things in the lab generally. But we need extra steps to go from grams. Say we had 5 grams of methane here. How many grams of water would we get? Well, we can't just do the 1 to 2 ratio because we're not in moles. We're not in molecules. We're in grams. Grams first need to be changed into moles. So that's what this conversion ladder sets up for you. So what you end up doing is you have your given substance as your starting point. How many grams of given? In the case that I gave you before, it'd be 5 grams of methane. The first conversion bubble you set up converts from grams to moles. And what we use is mm being the molar mass that you get from the periodic table. The second, so then we can cross out grams given here. The next conversion bubble converts us from, and this is the key one, this is the same conversion that I used up here. Because we had 1 mole of methane to 2 moles of water. And so this conversion does that. We have moles of the substance we want over the moles of the substance we're given. That's the ratio part. So now we can cross out moles that are given here and here. So now we know what the moles of the substance that we want to know, or usually we call it our unknown also. We want to convert from moles to the molecular mass, which we will measure in grams. So we have grams of the wanted substance. So by doing that, then we start with 5 grams of methane. Well, now we know how many grams of water do we have from this previous example. So in this last conversion bubble, we have the molecular mass, we have the moles that we want, we get that from the periodic table again. And when we cross out these units, we're left with the grams of water. And that's how we solve these questions. So let's get into an example or two here. Here's the first example. How many grams of silver chloride can be produced from the reaction of 17 grams of silver nitrate with excess sodium chloride? Now we're going to get really good at writing formulas from names, and so we're going to have to revisit that and take some time to learn that. Here is how we set it up. Step 1 is to write the equation. By the way, when we take the quiz, I'm not talking about that part on the quiz. It's the previous slide. So here we have 17 grams. This is our known substance, or the substance that we call from the previous slide here. Let me erase all of this now. This is the mass of our given grams. So here we are, silver nitrate. Silver nitrate is our given substance in grams. So the moles of the given substance now is silver nitrate, the molecular mass of silver nitrate, and the moles here of silver nitrate. Now, the part that we want to know is silver chloride, AgCl. So that's the wanted substance, AgCl, AgCl, AgCl. So that's the steps we're going to take. So first of all, we convert from grams into moles, and now we can cross out our units here. So now we're in moles of silver nitrate. Our next step involves going from moles of silver nitrate to moles of silver chloride. So now we can cross out this, right? Here and here. We can cross out the moles here and here, and we're left with just moles of silver chloride. But we're still not into grams yet, which is what we want to know. So this first conversion bubble here, the third one would be from grams to moles. So if we start crossing out these units now, cross out those two. Now in a different color, I'll show you moles of silver nitrate. Silver nitrate get crossed out. And then in black, let's go red here, I suppose. moles of silver chloride, moles of silver chloride. So we're left with our units as grams of silver chloride. Now all these steps we've done before. It's just a matter of kind of putting them together and sandwiching them together properly to make these work. Another example here. Tin 2 fluoride, SnF2, is used in some toothpaste. It's made by the reaction of tin with hydrogen fluoride. So here's our tin, here's our hydrogen fluoride. I've balanced the equation, written the equation for you. Here's our products. The question is, how many grams of tin fluoride are produced from the reaction of 30 grams of hydrogen fluoride? So this is our known. Our unknown, or the one we're trying to solve for, is grams of SnF2. So put your givens on top of the balanced equation. So what we would do then is we put 30 grams here, and we put question mark grams here, because that's what we're looking for. So again, solving for this, here's our 30, here's our x, the x that we're looking for. So we go from grams to moles of hydrogen fluoride using the molecular mass conversion bubble. Then we go from moles to the moles of this new substance, SnF2. And we use the ratios. So now it's a 2 to 1 ratio because there's a 2 here, there's a 1 here. And that's the critical part to understanding this conversion term right here. The third conversion bubble then goes from moles of this into grams of tin fluoride. And then we're done. And remember, anytime in these conversion bubbles, like this conversion bubble means that 1 mole of HF equals 20 grams HF. And so the top equals the bottom. That's one of the important parts to understanding this. If you don't include your units, it's going to be very complicated when you start crossing these things out. So that's what I've told you all year, include your units on these conversions, because now it's about to get real difficult if you don't do that. That's it for the slides. Make sure you go on and take the quiz for part 1. There's also part 2, but you don't need to do that until tomorrow or the second day of stoichiometry.